Hello everyone and welcome to another episode on this very channel. In today's lesson, we shall be looking at how we can find solutions to first order PDE using the method of what? Characteristics. Using the method of characteristics. If you haven't yet subscribed to the channel, kindly hit on the subscribe button for me. So let's get started. In our previous lesson, we discussed about how we can use the directional derivative approach to solve a first-order homogeneous PDE with constant coefficient, a first-order linear homogeneous PDE with a constant coefficient. So we discussed about something of this well form. We said that when you have a PDE of this well form, AUX plus BUY is equal to 0, where A and B are constants, then we can make use of what? The directional derivative approach to solve this. So we look at an example of this form: 3ux plus 4uy is equal to 0. So these are first order linear homogeneous PDE with constant coefficient. The coefficients are constant. If that happens, then we can make use of what? The directional derivative. Now what if these coefficients are no longer constant but rather variables? Let's say xux plus yuy is equal to 0. Since the coefficients are no longer constant, we can't make use of the directional derivative approach. If that happens, then we have to go in for a more stronger and then powerful method to help us find the solution to this PDE of this well form, where the coefficients are what? Variables. And this calls for what we call the method of characteristics. So to be able to solve a first order partial differential equation where the coefficients are variables, then we go for the method of characteristics. Now what is this method of characteristics? The method of characteristics is a special technique that is used to solve a first order partial differential equation. The method of characteristics, its main job is to convert or reduce the PDE into an ordinary differential equation. Now, once this partial differential equation has been reduced or converted to an ordinary differential equation, then we can make use of any of the methods that we know in solving ordinary differential equation to solve it. Or we can simply make use of our simple integrating technique to solve such ordinary differential equation. The method of characteristics can be used to solve a first order linear homogeneous PDE. So we have first order linear homogeneous and then non-homogeneous PDE. So you can use the method of characteristics to solve a PDE of this well form. It can also be used to solve first order nonlinear, homogeneous, and non-homogeneous PDE. So the method of characteristics, in fact, it is a very powerful tool. It can be used to solve many first order partial differential equation. Now, what is this method of characteristics equation that we are hyping so much? Now, this method of characteristics is giving us so this is the method of characteristics, which is given as dx all over this is equal to dy all over this, and then du all over this. Now we can simplify this. We can make it smaller and cute and write it as dx all over a is equal to dy all over what b is equal to what du all over f. Very, very easy. So this is the method of characteristics that we are talking about. Now this a and b are the coefficient of, let me write it as this. This a is the coefficient of ux, and then this b is the coefficient of what? Uy, and this is the function on the right hand side of the equal sign. So when you have, let's say, a PDE of this well form, here our a is equal to what? X, and then our b is equal to y, and then our f is equal to 0. From this example 2, our a is equal to 3, our b is equal to 4, and then our f is equal to 0. Very, very easy and then simple. We are not going to look at the proof of the method of characteristic, but we are going to look at how we can use this method of characteristic equation to solve a first order partial differential equation. We are going to look at how best we can use this equation to solve first order partial differential equation. Before we start with the examples, let's look at the steps that is going to help us solve a first partial differential equation using the method of what? Characteristics. So this is the step that is going to help us solve a first order partial differential equation using the method of characteristics. So the first one says that we have to first write the PDE in a standard form. So when the PDE is given, make sure you write it in a standard form like this. And then 2, form the characteristic equation. So you form the characteristic equation, form the PDE, and it should be in this real form. Now I form one equation if f is equal to 0. So if this f is equal to 0, we have these two equations left. That is only one equation. And then form two equations if f is not equal to 0. So if this f is not equal to 0, we form two equations. So we are either going to pair this to give us one equation, and then we come and pair this to give us two equations, or we come and pair this and that to give us our second equation. Very, very simple. And then IV, separate the variables if possible. So we are going to separate the variable using the separation of variable method if possible. And then V, we integrate the equation. So after separating the variables, we integrate. And then V, I define the general solution. And then the last one, we apply the initial condition if there is any. If we have an initial condition, we apply it. And then we are done. Very, very easy and then simple. So let's look at an example. So we want to solve the PD 4ux minus 3uy is equal to 0 with the initial condition u of 0y is equal to y cubed. Very, very easy and then simple. So when we look at this, we have 4ux minus 3uy is equal to 0. This is a first order linear homogeneous PD with constant coefficient. So we can make use of the directional derivative as well. We can also make use of the method of characteristics equation to solve it. Since we are looking at the method of characteristics, we are going to use the method of characteristics equation and then to solve it. So we have our solution. We are going to go by the steps here. So the first step is write the PD in a standard form. So you can see that the PD is already in a standard form. So we are okay with it. Then we form the characteristics equation. So before we form the characteristics equation, we have to first identify our A. Our A is equal to what? The coefficient of ux. So our A is equal to 4. Our B is equal to what? Minus 3. And then our F is equal. So once we have this, we form the characteristics equation. So we have dx all over A is equal to what? Dy all over B is equal to du all over what? F. So we have dx all over A. Our A is 4 is equal to dy all over B. Our B is what? Minus 3. So we have dy all over minus 3. And then we have du all over f. Our f is equal to 0. Since f is equal to 0, we have only two equations left. That is what? Dx all over 4 is equal to dy all over minus 3. So this is the equation that we are going to use. Since f is equal to 0. Now once we are done, it says we are done with this. Form one equation if f is equal to 0. So we have formed only one equation if f is equal to 0. Now we separate the variable if possible. So you can see that the method of characteristics, which is this one, has converted the partial differential equation into an ordinary differential equation. Now once we have this, we can use any of the methods that is used to solve an ODE to find the general solution to this. Now looking at this, we can make use of the separation of variable method. So you can see that when we do that, when we do a cross multiplication, this will multiply that. So we have minus 3 dx is equal to what? 4 dy. So you can see that we have separated the variables into the x and then dy. Now once we have we integrate both sides, so we have the integral of this and then the integral of that. So when we integrate minus 3 dx, minus 3 is a constant, so we can bring it out. So we have the integral of dx is equal to 4 is also a constant, so we can bring it out. Then we integrate dy. So when we integrate 1 dx, we are going to get what? Minus 3x then plus. Whenever we integrate a function, we add what we call the constant of what? Integration. So we are going to add the constant of integration. So we have c. And then it's equal to, when we integrate the y, we are going to get y. So we have 4y. Then we add the constant of what? Integration. But since we are having one, a constant plus a constant will still give us a constant. So we can decide to clean these very parts. So from here, let's make the constant the subject. So we have our constant is equal to 3x plus what? 4y. So this is what we are having now. Now since the equation 4ux minus 3uy is equal to 0, the solution to this is a function of what? The constant. So the solution to this becomes what? U of xy is equal to a function of what? The constant. Function of the constant. So our general solution is going to be u of xy is equal to a function of the constant. The constant is what? 3x plus what? 4y. Very, very easy and then simple. So this becomes our general solution. So this is what? Our general solution. But I can say that with the question, we were given an auxiliary condition or the initial condition. So we can proceed to find the particular solution using the initial condition given. So let's continue from here. So we have our general solution, u of xy is equal to a function of 3x plus 4y. And then we have the initial condition to be of this well form, u of 0y is equal to y cube. This means that wherever we see x in the general solution, we should plug in what? 0. So from here, you can see that our x is equal to 0 and then our y, let me write it here. Our x is equal to 0 and then our y is equal to y. So wherever we see x, we plug in what? 0. So we are going to have the general solution to be, this will give us 0 and then we have y and then move on to this part. Our x is 0, so 3 times 0 gives us what? 0. We are left with what? 4y. So we have the general solution to be of this form. Now let's write the initial condition under. So we have u of 0y is equal to what? Y raised to the power 3. Now as I said in my previous video, we said that when you have two equations, let's say p is equal to 0 and then q is also equal to 0, then we can say that p is equal to what? Q. So from here, if u of 0y is equal to this and then u of 0y is equal to that, we have two equations. Since this is equal to that, we can say that f of is equal to y cube. Very, very easy and then simple. F of 4y is equal to what? Y cube. So for me, what we are going to do is that we are going to find out what happened to 4y that give us what? Y raised to the power 3. So we are going to let any variable at all, let's say the variable p. So we have let the variable p be equal to what is in the function. So we have 4y. Now from here, we make y the subject. So when we make y the subject, we are going to have y is equal to what? P over 4. So we have p all over 4. Now once we have this, we substitute this into this equation. This equation. So we are going to have f of, we are saying that p is equal to 4y. So we have p, f of p is equal to, and we are also saying that y, is equal to what? P over 4. So we have P all over 4, and all of this is raised to the power of 3. Let me stand here so that I can write very well. Now at this very point, what we are going to do is that we are going to go back to the general solution. So this is the general solution. We come back here, we go back to the general solution, and then we pick what is in the function to replace what? The P. So we are going to have 3x plus 4y is equal to, we are picking what is in the general solution here to replace P. So we are going to have 3x plus 4y all over 4, and all of this is raised to the power of 3. So from here, we can write this as 3x plus 4y all over 4 raised to the power 3 will give us what? 64. So we have 64. U of xy is equal to, let me write it here, U of xy is equal to 3x plus 4y all over what? 64, and this is raised to the power 3. Very, very easy and then simple. Very, very easy and simple. Let's look at one more example. So we want to solve this partial differential equation using the method of characteristics. So for the steps that I wrote down here, the first step says that we should write this in a standard form. So we are going to write it in a standard form before we start. So we are going to have ux plus uy is equal to, this will move to the right hand side to become minus u. So once we have this, we identify our a. Our a is the coefficient of ux, that is 1. We identify our b is the coefficient of uy, and then our f is what? Minus u. So once we write this, we write the characteristic equation for this. So we are going to have dx all over a, our a is 1, is equal to dy all over b, our b is also 1, and then we have du all over f, our f is minus u. So once we have this, we form what? Per the steps, we form two equations when f is not equal to 0. Since f is not equal to 0, we are going to form two equations. So we have the first equation, or first pairing. So we have the first equation. We are going to take dx over 1 and then dy over 1. So we have dx over 1 is the same as dx, and then dy over y is the same as what? Dy. Now once we have this, what do? We integrate both sides. So we have the integral of that. So when we integrate 1 dx, we are going to get what? X. Then we add the constant of integration, that is what? C is equal. When we integrate 1 dy, we are getting what? Y. We can add the constant of integration, but since we are having constant, when we add a constant to a constant, we are still getting a constant. When you add 4 to 3, you are still getting 7. That is what? A constant. A constant plus a constant gives us what? A constant. So we can decide to clean one of the constants. We are cleaning this one. So from here, we can say that our constant is equal to what? Y minus x. Now, since we are having two equations, we are going to have two constants. So let's call this constant 1. Are you getting it? Very, very easy and then simple. So we have one of them. We can call it. Now, since f is not equal to 0, we are going to get two equations. Now we have the first one. Let's look at the second one. So with the second one, we are going to pair this side, the du, with any of this. You can pair du with this. You can also pair du with that. So let's pair the dy and then the u together. So we are going to pair. We have our second equation. So we are pairing du all over minus u is equal to what? Dy all over 1. So with this, you can see that we have separated the variables, right? So we have the u over u is equal to the y over 1, which is the same as what, dy. Let's eliminate the negative sign by multiplying 2 by negative 1. So we are going to be left with du all over u is equal to what? Negative dy. From here, we can integrate both sides. So we are going to integrate that with respect to du, and then we integrate this with respect to what? Dy. Now, when we integrate the u over u, we have a function and a derivative. So we can write this as integral of 1 over u du. Now, when we differentiate u with respect to u, we get 1. So we have a function and a derivative, and that gives us what? Length of what? U, a function and a derivative. So we are going to get what? Length u. We can add the constants of what? Integration. Let's say c2. We are going to add it to y, so let's clean this part. So this is going to give us minus y. Now, since we have length on the dependent variable u, we can also take the length on the constants we are going to add, the constant of integration, to give us what? Length c2, so that we can clear the length away. Okay, so from here, we want to make c2 what? The subject. We have c1 here, so we have to make c2 the subject. So we can decide to bring length c2 to the left hand side to have length u minus what? Length c2 is equal to what? Minus y. Now this is just natural log. So when you have, let's say, length a plus length b, applying some of the properties of logarithm, you can write this as length of what? A multiplying b. If you have forgotten, let's look at the normal log of, let's say, b to the base of a, let's say, plus log, let's make it minus log of c to a base of a. Now, applying the properties of log, we can write this as log to the base of a divided by what? B all over c. So we are going to apply this property of logarithm to write this as that. Okay, so we are going to have length, then we have u all over what? c2 is equal to minus y. Now from here, we can decide to take the Euler on both sides of the equation, so that this will cancel this, and we'll be left with what? U all over c2 is equal to e exponent negative y. Now from here, we want to make c2 the subject, right? So we are just going to do some cross multiplication, and then we move on some small algebra. So we are going to have our u is equal to c2 e exponent negative y. We are looking for c2, so let's divide both sides by e exponent negative y. So we have e exponent negative y, e exponent negative y. This will cancel this. We have our c2 is equal to u all over e exponent negative y, and we can write it as c2 is equal to u e exponent y in this form. Good. Now, once we have two constants, so this is one solution, this is also another solution. Let's call it b. So you can see that we have two solutions, this and then that, c1 and then c2. So what we are going to do is that we are going to merge them to form one solution. We are going to do what? Merge them to form one solution. So in merging them, one becomes a function of the other. So you can say that c1 is a function of what? c2, or c2 is a function of what? c1. When you have two solutions, one becomes a function of the other. So you can take c1 to be a function of c2, and then c2 to be a function of what? c1. Any one of them is accepted, okay? So what are you going to take? So this is c2. Since we are having the dependent variable here, which is u, let's make c2 a function of what? c1. So we are going to pick this one, c2 is a function of what? C1. So C2, what we have? We have U e exponent y is equal to a function of C1. C1, we have y minus x, y minus x. Now we have u here. We can try to make u the subject so that we will have a function of y minus x divided by what? E exponent y. So we have our u is equal to a function of x, y minus x. We can write this in an index form as e exponent negative y. So our general solution, which is a function of x and then y, will be given as u at x minus y is equal to a function of y minus x and then multiplying e exponent negative y. And this becomes what? The general solution to this partial differential equation. Since we were not given initial condition, we are going to end here, and this becomes what? Our general solution. Very, very easy and then simple. We are going to end here, and then in our next lesson, we are going to look at, let's say, 4 examples on method of characteristics. Remember that these 2 examples that we have done falls under first order linear homogeneous and then non-homogeneous PDE. Very, very easy and then simple. See you tomorrow. Bye bye.